All right, everybody, we're going to get started here. I know some of you have been logged on for a couple minutes. We just want to make sure if anybody had any questions or any trouble logging on, we gave them time to do so. So my name is Eric Hayden. I'm a meteorologist with the Weather Service in Morehead City. Really appreciate you joining us tonight. I know a lot of you have taken classes with us before. This is our advanced class, kind of our gift back to you, where we go more into the science. If you haven't been to a class before, we'll kind of do a basic review here pretty quickly, but this is our advanced class. We only do a few of these each spring season. As always, if you have any questions, you can email me. You will get a follow-up from me tomorrow, just a review of what to report to us, because that's really what is most important, not that you know all of the science, and you'll have my email for that as well. So I want to go over a couple items with the class. Some things have changed from year to year, so there may be some new things if you haven't joined us in a while. This is actually our 4th year of online classes. With everything going on, we're all virtual this year, but we've been really accustomed to that because in the past, we would do in-person classes, but we always had a few online versions because we just found that it was better for some folks to attend these from home. So we're pretty used to doing this. We mentioned that our presentation and also the course certificate is in your possession right now. On the far right, or however you have everything loaded up, you can actually download the presentation itself as a PDF. It's in the handout section. It's labeled Advanced Spotter Training Updated 2021. It's a big file, but you can certainly download that and review it as necessary. And the other thing that you'll notice in the handout section is that there is the option to download your certificate now, so you can go ahead and print that out. Both your audio and video will come through the personal computer or mobile device, so you shouldn't have to worry about any audio issues. And I can see that we have a few people commenting in chat that can see and hear us okay. So you should be okay in terms of video and any technical issues. I do notice that we do have one hand raised from Mitchell. Mitchell, if you have a question, just ask us in the chat. The presentation itself, you can enlarge the presentation. So if you have a mobile device, you can actually swap screens so that it's full screen me or full screen presentation. So probably want to go full screen presentation. If you're on a personal computer, you probably see me as a small image. If you have trouble viewing the presentation, you can expand it so you can see it full screen, because you certainly don't need to see me the whole presentation itself. If you have a question, it's on the right-hand side. You can ask the question in chat. Ask a question at any time. I'll briefly be monitoring it, but if it's a technical question with regards to what we're presenting, we will answer all those more than likely at the end. Unless I happen to catch it, it's just me tonight. Probably take all the questions at the end. I will monitor it now in case we have any technical issues. I can see Christian said that everything's looking good on that end. So I think we're good with the audio and any technical issues. If you, and Mitchell unraised their hand, so I can see that the question was probably answered. If you do, raise your hand for a question, we'll just call on you and unmute your microphone, and you can go ahead and ask it verbally. All of this is recorded from the sense of the presentation and myself, not your questions and not anything you say. We'll post the class on YouTube, so if you miss any of it, or if you have a neighbor or family member or friend that you think may be interested, certainly encourage you to share this with them. I mentioned that you can communicate with us through the chat. If you don't see what I'm talking about, there is a box. There should be a dialog box, and you can just open that up. And then on the mobile device, it's a little easier, but there's some settings on the bottom. You can open that up, and again, swipe left or right to increase the presentation size as needed. We mentioned in the very beginning, this is our advanced class. You should have already taken a basic class. Let's say you haven't. That's okay. Just know that this is much more in depth, much more detailed. Just to cover all our bases and to ensure that we're not missing anybody, we're going to do a quick review at the beginning. Then we're going to go more in depth. So just kind of keep that in mind. Comment in the chat. I'm kind of curious, is this your first time with a spotter class with us, or have you been to a spotter class before? So comment in the chat. It's private, only we'll see it on our end. And also comment where you're watching us from this evening. I see we have a few folks across Eastern North Carolina, also down in Georgia and across the rest of the United States. So I always like to see where people are watching us from. Like we said, this is our advanced class. We do have other classes, including the sister class to this, which is the basic winter that comes in the fall and upcoming winter of next year. There's a flood and tropical SKYWARN, and then it's not listed on here, but we do have some CocoRaws or precipitation training classes as well. So a lot of classes to offer, and the reason why we do that is we really want you to be a year-round spotter as much as possible. So again, go ahead in the chat and comment. Have you been with us before? And if not, just check in where you're watching the classes from as well. We always want to encourage you, whether this is your first class or your second or third, always check back with us every couple years, because while the severe weather pretty much stays the same, we do change sometimes the way we want you to report. We try to keep the information current and fresh, so we do try to keep things updated and relevant. You can always go to our website, weather.gov/Morehead City. Scroll to the bottom, there's a SKYWARN icon, and there's a lot of good information. What to report, when to report, our current schedule. Let's say you want to take a refresher class, and then we've got this tab called recorded training. This is where you can find all our YouTube videos. We'll certainly like you to keep relevant with that. So I see we're getting some comments in the chat. David has taken the basic and CocoRaws. That's really good. Christian asked, are we going to do a poll on that? I should do that. A poll would make it easier, Christian. That's a good suggestion for next time. Michael, thanks for your amateur radio help out in Maysville. Thanks for joining us tonight. Aaron said this is his third class, winter and basic in spring. So very, very good, or winter and basic, and this will be his third one. So Aaron, thank you for joining us from the Outer Banks. Sorry, Alan, in terms of the chat part, you got it right, because I see you. So Alan had mentioned up in Merriman and has already taken the basic class. That's great. Elizabeth, I like this. She was from the class that was canceled, ironically, due to severe weather. So that's only happened a few times. You'd think it would happen more with us scheduling this during the active season. So Elizabeth is doing it backwards. That's okay. Elizabeth, we're going to go over basic real briefly and then follow up with the basic, because some of it will sink in more. Mitchell commented, has done the basic and CocoRaws. So I really appreciate you joining us again. It's always good to have people come back. It means we're doing something right. And always tell other people that are interested in the program what we're doing here. So similar to the basic class, a quick overview on the Weather Service, a really quick overview of spotter procedures, because most of us have been through this. Then this is what separates us from the basic class. We're going to go over radar principles. We're going to talk about things like dual pole radar, precipitable water, some techniques we use in severe weather forecasting. And then we'll talk about supercells and squall lines. And we did that in the basic class, but we're going to take it a step further in terms of what we're doing with the education of that. So a little overview of the Weather Service. We're out of the Morehead City office. I know most of us are from Eastern North Carolina. We've got some folks joining us across the country. That's perfectly fine. I will encourage you to hook up with your local office. The reason why I say that is the principles are all the same. We want you to report. We encourage you to help us out. The only difference is the spotter number, the email they use, that will be different. So if you're in Indiana, we still want you to report large hail. The way you do it is going to be different, and that's where you want to reach out to your local office, mention that you've taken the training. You can show them the spotter certificate, and then they'll add you to their local database. So as I mentioned, we're in Eastern North Carolina. We're in Newport, technically. The biggest city nearby is Morehead City, and we cover the eastern quarter of North Carolina. That includes the Outer Banks, the Crystal Coast, and this yellow area for forecasts and warnings out to 20 nautical miles. We do watches, warnings, advisories, in addition to the forecast itself. So if you've ever been out on the waters, we do a marine forecast as well. The big thing about us is we are open 24/7. A lot of us are teleworking these days. I'm doing this class from home tonight. We always have at least a few of us at the office, or during Florence, it's the whole staff. So it just depends on the weather. we ramp up for bad weather. So the night that we canceled the severe weather, the last SKYWARN class, we had a lot of us at the office anticipating bad weather. We are a reinforced building, so we're a brick building with hurricane shutters. So we're made to stay safe. We're up high, we're at a safe location. So when hurricanes and storms go through, we will be okay. The best way to get our information is our website, weather.gov/Newport/Morehead City, a bunch of different ways to get to it. If you're watching us from outside of North Carolina, just remember weather.gov. Click on the map where you live and you'll get a local forecast just like this. It'll just be from your local home office that we showed you on the first slide. The 7-day forecast is real detailed in either text or icon, and I always encourage people to scroll down the page, click on the hourly weather forecast, especially if you want more with regards to specific information. All right, a couple more slides and we're going to get to the advanced class, or the advanced portion of the class. To refresh your memory, and for those that are new, the SKYWARN program is really all about volunteer. It's an organization that helps, it's run by the Weather Service to provide us ground truth reports of bad weather. And ground truth just means what is actually happening at the ground. We've got GOES 16 and 17 satellite, phenomenal technology, can update every couple minutes. Doppler radar, dual pole enhancement many years ago, phenomenal technology. But keep in mind with the radar specifically, we're looking up in the sky. It's detecting hail, it's detecting strong rotation. It's very, very accurate, very precise piece of equipment, but it's looking up in the sky. Is that making it to the ground? Is the hailstone melting? Is it still the size of golf balls? Is the tornado reaching the ground, or is it just a funnel cloud? So those are the types of things that spotters really help us fill in the gaps, really to determine, is it actually happening in the community? And this adds credibility. We mention this all the time. We get a lot of warnings. If a person sees that it's impacting a town near them that's relevant and something that, hey, it's the next town over, they're going to take it much more serious. So these spotter reports are crucial. No report is not worth calling in. So please keep that in mind when you make those reports. So review on what to report: tornadoes, funnel clouds, any flash flooding, storm damage, hail, wind speed, and rainfall amounts. We're going to go through the two most popular ways to report in. I just want to backtrack. Tornadoes, we've talked about this before, has got to have rotation. We went over it more in the basic class, but it has got to have rotation. If it's in contact with the ground, it's a tornado. If it's not in contact with the ground, it's a funnel cloud. Keyword: rotation. You can have dark, low-hanging clouds that are triangular, but if they're not spinning, it's not a tornado. Any size hail, try to measure it with a ruler or use a reference. Don't use marbles, use a coin, penny, quarter, that type of thing. Take a picture if you can. We love getting pictures. That really gives it a reference. A hailstone looks impressive in a picture, but if you put it next to a quarter, that gives us a gauge for how big it is. As far as rain and flash flooding go, rainfall amounts over a couple inches in a short period of time, or 24 hours is what we're looking for. And then as far as flash flooding goes, or even coastal flooding, we're talking about something significant. So if you live along the coast, you get coastal flooding from not just hurricanes, but also nor'easters. If it's something you only see a few times a year, if not every few years, we want to hear about it. How deep is it? What's inundated with water? What roads are closed? That type of thing. So that's just kind of a summary. I have got wind speed up there. You don't have to have an anemometer, but with that, we're talking about tree branches down, any type of damage. So you are the eyes in the community. What is damage? Uprooted trees, that type of thing. Most important part of this class, much like the basic, is the 800 number. We have email, Facebook, amateur radio, a lot of ways to report, but we don't always have those ways available to us in terms of responding to it. So for example, could you send us a Facebook message or email? Yes. Will we get it? Yes. Will we get it right away? Probably not. It just depends on if we have it up on the screen at the current time. A telephone call, we get right away. We're always answering our phones. We don't turn them off. It's an 800 number with multiple lines, so it rings through. So please, especially for severe weather, call this 800 number. Snowfall and things like that are not as time sensitive. You could do another way, but I want you to get in the habit of the 800 number. And we can ask you questions. We can say, okay, you're reporting a tornado. Is it, or let's say a funnel cloud, is it actually rotating? Okay, it's a low-hanging cloud, but it's not rotating. Okay, that's probably a scud cloud, something along those lines. When you call in, or any way you report, say who you are, what you saw, where you saw it, and when. The timing is very important. Let's say you took shelter in your safe room, which is a good thing to do, and then you report 10 minutes later. There's nothing wrong with that, but we need to know that so that when we're matching it up to the radar, it makes sense. So please keep that in mind. Another good way to report, especially follow-up pictures, videos, more detail, is our email, wxobs.mhx@noaa.gov. I've got that little disclaimer in there again. I know we've got some friends from outside the area. There's no problem with that. Just keep in mind, while these procedures are the same, your reporting is different, because if you're in Texas or Georgia, they're not going to have this email address. It's going to be different. So contact your local office and get hooked up with them. So before I go forward anymore, I'm just going to make sure we don't have any more questions in the question box here. I appreciate all those that answered where they've taken the class from, so that's really good. And I don't see anything. And Elizabeth, hopefully that was a good refresher or a good base level, so you're not too far behind. But Elizabeth and others, you can take the basic class now online. We've got it posted, or you can sign up for one of the future ones to do it live. So that's not a problem at all. So this is the advanced class. We want to show some more principles. We're not trying to teach you to be a meteorologist. You don't have to know any of this to make a report. We do this as a thank you. We really appreciate you taking the time. I know the evenings are getting lighter and later. We really appreciate you taking the time to learn about weather and make reports with us. So we kind of want to give back and give you a little bit of something that you might be interested in. So that's what the advanced class is all about. It's not about knowing everything. It's just about knowledge, and just you may find some of this interesting. Obviously, you did enough to sign up for the class. So we'll get going with the radar itself. When you think of a radar, once we get back to whatever normal is, by the way, you're welcome to visit us at the Weather Service. We're on Roberts Road in Newport. Looks like a giant soccer ball up in the sky. That's the protection of the radar. But inside, it's actually a satellite dish, and it's spinning around, and it's sending out a beam of radiation into the sky. And most of the time, it's listening. Does that bounce off any particles, like a raindrop or snowflake or even an insect? It will get sent back to the radar based on like a certain intensity, and that's how we can measure intensity. But we can also tilt that satellite up into the sky so we can get a cross section of what is happening above us. So that's real important to remember. So in this diagram at the top, the triangle, the yellow triangle represents the radar, and this lower yellow line is the lowest that the radar can go, and this is 0.5 elevation. So the radar's angled up. It can never go below 0.5, and while it can tilt up and tilt down, it never drops below the 0.5. So because the Earth is curved, the farther and farther you get away from the radar site, you actually get higher into the sky. So in this example, this storm that's close to the radar is well sampled, is what we call it, because we can see most of it because it's close to the radar site. However, in this example on the far right, this tornadic storm by the diagram, it's farther away, and since the Earth is curved, even the lowest beam of the radar cannot see that circulation as well. So that's, kind of re-emphasizing we have a lot of technology, very useful, and we can use satellite and other things in the absence of difficult things on radar, but spotters really help fill in those gaps. The example on the bottom is the whole radar pattern that we have. So the lowest elevation, measures this part of the atmosphere, but all these higher tilts can show us very, very high up into the atmosphere, seeing things like hail or strong winds that might be at 20, 30, 35,000 feet before it descends down to the ground. So it's pretty neat to be able to see those signatures high up in the atmosphere before they actually happen. So this example here is talking about the different modes of the radar. The one that you're probably most familiar with is reflectivity. This is what you see with your favorite meteorologists on local TV. You can see this on the Weather Channel, AccuWeather, Weather Nation, whatever your favorite is, or any of your favorite weather apps. On the left is what you see. The intensity is measured by on the scale. You'll usually have some type of scale. So darker reds and yellows and pinks indicate higher intensity, and the light greens, or in this case blue, lower intensity. So this is the description I was talking about. The radar is really a satellite dish, sends out a radar pulse, a radiation, and it's bouncing off targets or it's not. So if it's not, it just goes on out and we don't have any return to the radar. If it bounces off an object like a raindrop or hailstone, it's scattered back to the radar, the receiver part of the radar, and we can measure the intensity. We call this the reflectivity. This is what you're usually used to seeing, on TV or your local app. So using that reflectivity, we can see things like hail. Think back to the last one where I said the radar is, 0.5 elevation or higher. It can go higher or lower, kind of that slice of the atmosphere above us. If we look above us, we can see higher reflectivity, higher intensity, and if it's above the freezing level, we're talking, in the summertime, usually 14, 15,000 feet, then it's not water, it's ice. And if it's ice, it's a hailstone. So if we see something like this, this is a radar image, a cross section on the far right, where this white is very, very intense particles, in this case, rain down by the surface, maybe some hail. But if you're getting up 15, 20,000 feet, 25,000 feet, that's well below freezing. That is ice in the form of hail. This is what's known as a three-body scatter spike. So the radar itself will actually show us different principles, how the radar will look in terms of how we can detect hail. That's used to be a really good sign of large hail, but now with our increase in resolution, we see those a little bit more often than we did before. So pretty neat stuff. So the first thing I talked about with the radar was all about reflectivity. You're used to that. Hey, Eric, I've seen that before. It's kind of interesting. What else is there? The other really cool part of the radar is the Doppler part. The Doppler effect, there's a change in frequency that can be measured, and the Doppler effect is, you've noticed this if you've heard a train, as it's approaching, sounds different than as it's leaving away. Well, in terms of radar, the radar can actually measure winds blowing toward and away from the radar site. So the radar never shows us an actual tornado. It doesn't say this. It doesn't show a tornado per se. It shows strong rotation. If we see strong rotation and the environment is right, that we think it'll get down to the ground, we will issue a tornado warning. So here's an example of a bad tornado, probably the worst one we've had in recent memory. It's going on 7 years now. Luckily, we don't get a lot of EF3s, but we can get them. This is in late April 2014 in SKYWARN. So on this radar image, all of the red is the winds going away from the radar site. And so on this map, it's probably hard to see, but we're off the map. Down here in the lower right would be the radar. So all this red, these winds are blowing to the north. All the green, the winds are blowing to the south, so in opposite directions. So you might say, well, Eric, there's a lot of red and green up here. Why aren't you worried with that? It's got to be co-located with the storm itself. So it does show, that there's some air coming together here, convergence. But what our eyes are drawn to is something where it's real tight. We call this bright and tight. You have a red right next to a green, and you have a thunderstorm to lift that updraft, or that updraft to lift that rotation. It's very likely that you have a tornado. So here's a little zoomed in perspective. So again, on the left is something that you may never have seen before. It is the velocity. So the red is, in this case, is blowing from south to north or away from the radar. The green is blowing from north to south in rough terms. So very, very strong rotation here. And it's co-located or, along the same area as some high reflectivity and even a little bit of a hook. A hook echo is just showing the reflectivity is actually, the radar is showing the reflectivity wrapping around that circulation. So it's a decent indicator that it could be tornadic. Not all the time, but it's showing rotation. So that's what we look for on radar. So just kind of curious in the chat, and Christian will have to remind these. He's a frequent attender of these classes to do poll questions, so I don't have to always just ask you in the chat. But you all seem to be doing the chat well. Just out of curious, have you ever seen the image on the left before with regards to reflectivity? Have you ever seen a different radar image like that? So you can just comment in the chat. I'd just be curious to look. I like to keep these classes as interactive as possible. So Elizabeth has seen that. So I know some local meteorologists do show it. Christian says not sure. David has. So more and more folks are seeing it. I know the Weather Channel does a good job. Our local meteorologists do a good job. I used to be in television, and it was hard to show those images because you're trying to explain it in a real dire situation, and you don't want to lose people. You just want to make sure that they seek shelter and don't worry about the science too much. So Mitchell mentioned the storm by Wilmington, saw it. So yeah, some people have seen it. It's something that they show on TV only in tornado situations usually, and you have to be a real good explainer of it because you don't want to confuse people in a dire situation. So that's a little bit on radar. Went over base reflectivity. We went over velocity. Now I want to talk about an upgrade that we had. I think it was 2012. It's been a while now. I'm surprised it's been this long, but it was an upgrade called dual polarization. And it was a real big upgrade because prior to that, with conventional radar, the beam would go out from the radar. This is a great diagram because this is what the radar looks like. It's on a tower, looks like a giant soccer ball. But prior to the upgrade, the beam or the pulse that it would send out and transmit was only in the horizontal. With the upgrade to dual pole, we would see both the horizontal and the vertical that would come back. So kind of describe it more like a 3D effect. So we would have a much better idea of droplet size. How big is a hailstone? Much more accurate. Is it a hailstone? Is it a wet snowflake? Or especially in the wintertime, snow, sleet, wet snow, that type of thing was more easy to distinguish. And that helped a lot with our rainfall estimate as well, because we could see different things that would tell us, is it a big fat raindrop? Is it some drizzle drops? Those types of things. So we got a bunch of new products, things called differential reflectivity, correlation coefficient, specific differential phase, a lot of fancy names, and you can read what they all mean, and you have your PDF to really look into it. I'm going to focus on the one I'm most comfortable with because it's the one I use the most, and it's easiest to really, for me to understand in like a warning operation sense real quickly. That's called the correlation coefficient. It's the degree that everything is the same, homogeneous. So it's not mixed up, it's of the same likeness. We love this hail, tornado, debris, and also wintertime for distinguishing between the rain and snow line. Really good stuff. So there are things that the radar can detect besides just precip. We mentioned hail, raindrops, snowflakes, and things like that. There's birds, insects, anything else that flies we can detect. So we can see birds taking off. We see this a lot with our coastline, and at sunrise or near sunrise, you'll see these concentric circles on the radar. They expand and go get higher and go away as they fly off in the mornings, especially in the spring and summertime. And they have irregular shapes. So it's important to have these distinguishers on radar so we can tell what is real. And birds and insects are real, but I mean between things that we would be concerned about in meteorology and not. So that's where the correlation coefficient really comes in. And so I'll give you some examples of that. If we have anything correlation coefficient greater than 0.97, it's very uniform. It's all rain, it's all snow. Once that value starts to drop below 0.97, that means we're getting some mixed. So it might be hail or melting snow. And anything less than 0.8 is non-meteor. It could be debris. We'll talk about that in a second, or it could be birds and insects. I don't expect you to know these numbers or remember these numbers, but I want to show you this, then I can show you the pictures, because to me, the pictures speak volumes. So this is a correlation coefficient. This whole magenta, maroon shaded area is greater than 0.98. So everything in this area, whatever it is, and we would use other things like temperatures, dew point, surface analysis to determine what it is, but it's either all rain or all snow in this picture. On the edges here, it's more, it's some other thing than a rain or snowflake, because you can see that the colors get all crazy as the values drop off. So bottom line with this, it's all one consistent thing. Versus this, not all consistent. So some type of biological, or it's not a raindrop or hailstone type of thing. So this shows up a lot with birds and migration and rain. So this is a still image, so it's kind of hard to tell. But these darker areas of green and yellow is rain. But how do we know what all this is? Now, as a meteorologist, I know we get a lot of what's called ground clutter that shows up, especially at night and early in the morning. The beam of the radar will kind of bounce off the inversion, and we'll get some of this. But to a pilot or to a broadcaster that may not have been in the career for a long time, they might see this, and anything green or blue on the radar is precipitation, and that's not the case. If we put on the correlation coefficient, it stands out more. Remember that all maroon color means all consistent, either rain or snow. So in this case, here's where the rain shows up, and in this case, these are the birds I was talking about in the morning. So pretty cool stuff. A lot of the weather apps for radar, you can display the correlation coefficient and see some of this stuff. So what does this mean for specifically severe weather? I mentioned we really use it in the wintertime as well, because if you have a rain snow line and you have all the same correlation coefficient north of a line and all the same correlation coefficient south of the line, where it's in between mixed particles, it's your sleet, your freezing rain, your snowflakes. So you can actually see this line march across the area. North of the line is all snow, south of the line is all rain. So we can quickly determine the rain snow line with using the correlation coefficient. But with the severe weather, we can also use it to detect debris. Remember, raindrops, snowflakes, something all uniform is going to show up as really high. But once you start to get mixed precip, rain and hail, the correlation coefficient is going to drop. And then in some cases, if it drops a lot, it could be debris that's being lofted up from a tornado. So this is an example of that. Here's what you're used to with reflectivity. Again, very, very bright. Here's what looks like a hook echo, but there's really high reflectivity right here, and we'll explain what that is here in a second. Here's our storm velocity, storm relative motion. Again, strong winds away from the radar, strong winds toward the radar, and here's that bright and tight couplet. So in the past, we would see that. We would obviously know it's very likely a tornado. The higher reflectivity is probably an indication of debris, but we weren't sure. You weren't as sure until dual pole came out. You can see what this is called a correlation coefficient drop in that. And that's a likely indicator that there's debris being lofted up, whether it's, unfortunately pieces of houses and stuff like that is actually showing up on the radar. But it always has to be put into context. Sometimes I've seen some stuff on social media where people will look at an image of just correlation coefficient and they'll see these other areas where the values are non-uniform, and they'll automatically assume that that's debris or it's any other thing. All this means is uniform or not uniform. but you got to put it in context. So yes, this area is non-uniform, but you have to put it in context that it's also where there's strong rotation, also in context where there's strong reflectivity, also another sign of debris, and that would lead you to higher confidence that unfortunately in this case, the tornado is on the ground. So that's where technology has increased. We rely on spotters to confirm it, but if it's really bad, unfortunately now the technology is getting so good we can actually see the result of the tornado. So in this case, we would like to have the warning out before it happened. Then when we see something like this, it's a bad situation, but we can convey that information in a warning. We can say, look, the radar has confirmed it, you know, and hopefully people take it much more serious. So that's as in depth as we go on radar. It's a balance. We don't want this to turn into a Weather 101 class because that's not our mission. Is protection of life and property, but we want to give you a little something more than the basic, just kind of as our treat. So following up on the basic, the next part of the class as we kind of get toward the last maybe 40% of the class is a follow-up. So some of the concepts, it's more like version 2, the second version of it. So we're going to talk a little bit more about lightning, high winds, hail and tornadoes. You heard about it in the basic class, but we're going to go more in depth on this. Back on the basic class, remember we mentioned a severe thunderstorm is one that produces 58-mile-per-hour winds or greater, and or hail 1 inch in diameter. We mentioned that before. That's about where we start to have some damage, either crop damage due to the hail or even your house. And winds, that's where you start to get some larger branches that are blown down. We mentioned this in the basic class, and I'm just saying this as a refresher for some of us, and some folks are new. We talked about instability. That's fuel for the storms. A lot of times we get our fuel from the storms from a really warm and humid atmosphere, and it's really cold higher up, or cold air is coming in. Think about the storms we had last night. We didn't necessarily get severe storms, lightning, heavy rain, yes, but remember how warm and humid it was yesterday? You know how cool it's been today and how cold it's going to get tonight. So it's usually that clash of air masses that will lead to that increase in instability. We mentioned moisture, lifting mechanisms, and also some sort of trigger and shear. So we're going to cover those a little bit more in depth. We mentioned that instability is really the fuel for the storms. You know, cold air versus warm air. Warm air, those particles are moving around, less molecules per the area, so it's actually lighter air, it's more buoyant, it naturally wants to rise, and that can cause you know, the cloud or the air to cool, condense, form clouds, and kind of leads to that whole process. We mentioned this before. For the atmosphere to be unstable, it's really good to be a hot and humid day, so you're really warm at the surface, and then as you go up in the atmosphere it gets colder. That is an unstable atmosphere because the air parcel that's warm, as it rises, it's encountering colder and colder air, so it's going to want to accelerate quicker, and that leads to more instability. The reason why we talk about this is it is really a good measure of the potential for a storm. And one way we measure potential is something called CAPE. We love acronyms in meteorology. So CAPE is called convective available potential energy. It is the potential that the storms have to become severe. It's not a one-to-one. It doesn't mean that potential is the key word. It doesn't mean you're definitely going to get severe weather. And I'll give you a for example here in a second. But generally speaking, if we get a couple hundred, and this is J over kJ, G is joules per kilogram. If we get a couple hundred joules per kilogram up to 1,000, we're probably going to get some thunderstorms, maybe severe. That was last night. Enough energy to get the storms, not quite enough to be widespread severe, luckily. Once you, and this is rough rule, once you get up to 1,000 to 2,500 joules per kilogram, more likely for severe weather. That's kind of the sweet spot. And then very rare, but can happen. Well, I shouldn't say very rare. Rare to have this along with all the other ingredients, thankfully. You get above 2,500, major severe weather outbreak can happen, especially if you have the other ingredients. So a few asterisks. In the wintertime, it usually only needs a couple hundred joules, 200-300, and we can get some severe weather. And if there's a strong cold front, it can produce wind damage. So that's one asterisk. The second asterisk is there's many days we have a couple thousand joules of CAPE in the summer. If you've lived here, it's hot and humid almost every day, right? So we have tremendous potential for storms, but it doesn't happen every day. We're going to talk about it, but you need that trigger to put it all together. You can have all the potential in the world, but unless you act on it, it's not going to happen. But our sea breezes and river breezes and things like that, those are usually enough of a trigger to create those types of storms in the summer. So this is a map from the Storm Prediction Center. Tomorrow with a follow-up, I always like to do a follow-up to just, reconfirm what we want you to report to us. I'll include some links, and one of them will be what's called the Storm Prediction Center. They're out in Norman, Oklahoma. It's part of the Weather Service. They, in coordination with the local offices, will issue tornado watches and thunderstorm watches. They also do what's called a meso-analysis, and you can look to see what the parameters are for the upcoming day. This is an example of, it says ML CAPE, that's mixed layer CAPE. And these are, don't worry about the blues and the dashed lines, but the red lines are what you can focus on. So in this example, 2,500 joules of CAPE across central Illinois. This contours 2,000. So just looking at instability, you have to look at everything else. You need a trigger, you need moisture. But just based on instability, is there fuel for storms in Illinois? Yes. So one of those checklists we can check off. And in the basic class, I like to describe it as a recipe. You can't skip one of them. You need the oil and the eggs and the water for your cookies or your brownies. You can't just forget one, because if you do, it's not going to taste right. Same thing with the environment. So yes, we have instability today in this example from the past. Doesn't necessarily mean storms, it just means the potential is there. So that's when we start to look at other parameters to see what's shaping up. And the reason why we look at instability is the more unstable you are, as you get 1,000, 2,000, 3,000 joules of CAPE, the higher the air is more likely to rise, and that's called an updraft. So if you have a really strong updraft, you have the potential for more large hail, damaging winds, that type of thing. So for example, an ordinary thunderstorm, the air is moving 30 to 50 miles per hour upward. Whatever comes up must come down at some point. That's where you get your breezy, normal thunderstorms. There's lightning, heavy rain, the wind picks up, and that's it. Not a huge deal. True severe thunderstorms, the updrafts are moving 50 to 70 miles per hour. That supports quarter-size hail, 60 mile per hour winds, because again, strong updraft, strong downdraft as the storm collapses can produce those strong winds and hail. And if you get above 100 miles per hour with like a supercell, again, you have a water drop that's falling down because of gravity. It gets lifted up in the cloud because of 100 mile per hour winds. It's going to continue to go up and down, and that hailstone is going to grow larger and larger and larger. To get baseball size hail or golf ball size hail, that's a real heavy stone. Hail happens, a water drop falls, a water drop gets raised up into the cloud because of the updraft. It freezes because of gravity. It falls, and if it continues to do it over and over again, that's how it gets larger. Well, you're not going to do that with a 30 or 50 mile per hour updraft. It has got to be strong. It's got to last maybe 15, 20 minutes in the cloud to grow that large. And that's why we really look at instability a lot to see, are we even in the ball game? Do we even have fuel in the car to drive to the next town type of thing? So first thing we look for is instability. We measure that by CAPE. However, you need moisture and you need these other ingredients for it all to come together. So one way we look at moisture is through a parameter called precipitable water. We usually have plenty of moisture because we get it off the Gulf of Mexico, the Atlantic Ocean, but moisture does help in a lot of ways, not just because of clouds, but it actually increases the instability, more fuel, and it increases the strength of the updrafts, better support for winds and hail. So moisture is really, really important. And you might say, well, how does moisture increase instability? So this table shows dry air versus moist air. Most of us probably know this. 78% of our air is nitrogen, 21% is oxygen, and then this down here is water vapor. Water vapor, in terms of weight, is lighter than air. So the more water vapor you have, it's actually lighter compared to the surrounding air near it. So moisture plays a critical role, not just in terms of, hey, do we have clouds or not, but we mentioned updraft strength and also the increase in instability. So the other point was it increases the updraft. When moisture actually condenses to form clouds, it adds more heat. We mentioned, warmer, more humid environment creates more instability. So it's a nice cycle. And you can kind of see how these are intertwined together. So moisture is important, got to have clouds for thunderstorms, but it actually helps to increase the instability. And in the prior slide, it's actually lighter, water vapor is lighter than air, so it increases the instability. We do measure this. It's called PWAT, P-W-A-T. Again, we love acronyms. It's called precipitable water. That's how much water is above us, kind of in a column in the atmosphere. We measure this in inches. Usually 1 to 2 inches of PWAT is fine for thunderstorms. We are commonly over 2. This is why we commonly, if we don't have flash flooding, it's because of our topography. We're not really hilly. We got a lot of sandy soil, but this is why we commonly get downpours. If you've lived here in the summer, you know it just doesn't rain a little bit. It either doesn't rain at all or it comes down in buckets. And that's because we're usually pretty humid, so our precipitable waters are quite high. So this is back to the same image or same location of the image from the Storm Prediction Center. We're not looking at Cape this time. We already said that Illinois has a lot of fuel for storms. Now we're going down on the checklist. Do they have enough moisture? Looks like they do. These lines are precipitable water. We mentioned 1 to 2 inches is sufficient. 1.1, 1.2, 1.4. So kind of in the same location, about 1.4 inches for precipitable water. So do they have instability? Yes. Do they have moisture? Yes. So far, this particular day from our example from the past, looks like Illinois is under some risk of weather. The last ingredient they need, at least for a thunderstorm, we'll get to shear in terms of severity, is you need something to make it happen. You can have the instability, you can have the moisture, but you need a trigger. And we talk about this in all our classes. Cold fronts are the traditional one. You can get storms on a warm front. We'll talk about that in a second. But a cold front, very, very dense air pushes in and abruptly lifts the warm air in place. So apples to apples, you get taller storms with a cold front, 40, 50, 60,000 feet, perhaps in the summertime. So that's where we tend to get our most vigorous storms. One other thing to mention, as we slide and transition to warm fronts, the opposite happens. The cold air is in place, the warm air comes in, and it gradually rides up over the surface. So it's more a gentle slope. So you tend to get showers, you can get thunderstorms, and it tends to be a flatter storm. So they tend to not be as vigorous or tall. So you usually aren't going to get, really, really big hail or gusty winds and dramatic storms that you do with a cold front. There's always an asterisk. However, with a warm front, there tends to be a lot of shear. And we're going to talk about that in a couple slides coming up. So you can still get tornadoes, you can still get some bad storms. Some of the tornadoes that we had a couple weeks ago up towards central North Carolina was along a warm front. Again, the storms are not tall, but because there's a lot of different wind and shear along a warm front, you can get some tornadoes and some nasty storms. Another type of lift we like to talk about in the Carolinas, especially the western part of the state, are mountains. As the air flows toward a natural barrier, it's forced to rise up, so that can create, clouds and also thunderstorms and things like that. One that we get here a lot is outflow from other storms. A normal thunderstorm, it ingests warm, moist, humid air. It goes up as an updraft, and then the downside of the storm, the exhaust, is a rain-cooled air mass. Gusty winds, maybe a little hail. When it hits the ground, as it spreads out, it acts like a little mini cold front. We had this last night, watching the line of storms to our west. If you stare at the radar, you'll see this thin little line. It's really measuring a change in density, or it's not precipitation, but the radar can detect it. You'll see this little thin line moving out ahead of the thunderstorm, and those can generate new thunderstorms. So it's a pretty neat feature that can help generate new storms. And the one thing I don't have in there is the sea breeze. Down where we are, we can certainly get sea breezes, and what that is it's a pressure difference because of the temperature difference. So the water is cooler than the land. Land heats up, that's low pressure. Water's cooler, that's high pressure. And things like to flow from high to low. So you get this natural flow off the ocean. Island breeze, sea breeze, mid-morning, we get it pretty much every summer day. Unless a cold front or some weather makes or disrupts the winds, we get sea breeze pretty much every day. As it comes in, on the water-based side, it's cool, it's moist. On the land-based side, it's hot, it's dry. Different clash of air masses, boom, along those sea breezes, you can get storms. So we talked about instability, we've talked about moisture and lift. If you have those three ingredients, that is enough for thunderstorms. This is the advanced class. So we're going to throw a fourth ingredient, wind shear. You don't have to have wind shear for a thunderstorm. You want wind shear for a severe thunderstorm, and that's why we want to talk about it during this class. I briefly touched on this in the basic, but wind shear happens in two different ways. Number one is called directional. This graphic on the left is just demonstrating that if winds down where we live at the ground are from the southeast, and they shift into the south, southeast, southwest, and then a couple thousand feet up, they're from the southwest. That is changing direction with height. That can support severe weather. We'll talk about why. Another way that you can get shear is speed. Instead of changing directions with height, and again, height, I mean going up in the atmosphere, you change speed. So in this example, light winds at the surface, but as you go up a couple thousand feet, the winds get really, really strong. Either directional or speed can induce a rolling or twist in the environment. And that's important because you may jump to, hey, that's a tornado threat. Yes, more shear can make tornadoes more likely, but at a basic storm level, shear just by itself with a thunderstorm determines what type of severe weather we're going to have. So for example, instability, CAPE, if you have really, really high CAPE, you have a lot of potential, but it depends on how much shear you have to determine if we're going to get an organized outbreak with supercells, or is it going to be unorganized. So for example, if you've got some decent instability, the wind shear is it's okay. You're going to have single cells, multiple cells, kind of unorganized. We call this pulse storms. There's not a lot of shear, so they pulse up and they collapse on themselves. If you have more wind shear to go along with it, the storm is tilted. And because it's tilted, it's always grabbing warm, moist air. It's sucking in new energy. It can maintain itself. You can get squall lines in multiple cells because it's tilted. Instead of being in the vertical and collapsing and that's it, instead of being a 20-minute cycle, it's tilted and it can last an hour. And at the far, far end, if you have a lot of instability, a lot of shear, you can get supercells where it's its own storm. It just plows through and it can last a long, long time. That's where we can get the largest hail and the best chance for tornadoes. So we measure shear a couple different ways. One of the common ones in our forecast discussion will say 0 to 6 kilometer shear. That's a certain depth of the environment we're looking at. Anything better than 30, 35 knots is good. More than 50 is certainly dangerous. And again, you got to give it context. We've had many days where there's a lot of shear and nothing happened. Well, we didn't have the instability or moisture. It's got to line up. And luckily, it's got to line up, because that's why it doesn't happen all that often. And we look at different levels. Sometimes we'll look down near the ground. If there's a lot of low-level shear, it's more of a tornado risk day. If a lot of the shear is up in what we call the mid-levels, it's more severe thunderstorm day, not necessarily producing tornadoes. We already kind of covered this. Again, weak shear. I like to back up pictures, vary in the vertical, single cells, but as you progress to the right, more shear makes it more likely to last longer. Here's the developing stage of a thunderstorm. As it just starts to begin, you can kind of think of this as a baby thunderstorm. Again, the clouds are growing. You've got rising air. This purple line is the 0 Celsius, but 32 degrees Fahrenheit, maybe a little bit of hail at the top of the storm. The mature stage of a thunderstorm, you have a nice inflow to the storm, a nice towering cumulus cloud. The exhaust of the storm is usually the front side. That's the dark side where we have gusty winds and some hail. If you have a pulse storm, we go from the beginning stage to the mature stage to the dissipating stage, 15-20 minutes. The updraft forms, it looks great on radar, collapses, and that's it. If we have shear or a supercell, we're going to have a storm that lasts a lot longer. So that's a good thing to remember. So we're at about the hour point. I see we got a couple questions in chat that we'll answer. It is almost question time, so you guys are almost at the end. This is a little longer than our basic. I know Elizabeth, we've got on. By design, our basic is about 45 minutes because we don't want to lose anyone. Our basic class is report, report, report. This is how you do it. The advanced class is completely the opposite. So if this is too much for any of you, don't worry. This is where we stop. So so don't worry about that. So a couple last things, and we'll get to your questions. A really intense thunderstorm, again, strong updraft, can also have a strong downdraft. We will call these microbursts. So if you've ever seen on the news a lot of damage, high winds, and they called it a microburst. What is a microburst? It's just a fancy term for that descending rain-cooled air. And it doesn't sound crazy, and it does. Sometimes we'll do a storm survey and folks will think it's a lot worse if we call it a tornado versus, you know, a downburst. So we'll show you some examples of this. This is what we might see on a storm survey, especially if we do an aerial survey, if we've got some aerial photos. Lots of trees down. Folks will say it had to have been a tornado. What could cause all that damage? But notice the black arrows. These trees are kind of fan-shaped or divergent. They're flattened. We say laying in the same direction, but you might say, well, Eric, those are opposite directions. And you're right. They're divergent. That is conducive to a microburst. Doesn't mean it's any less dangerous. Can still be 100-mile-per-hour winds. But sometimes people have this fixation that if it's not a tornado, that it wasn't like a big deal, and that's just not the case. So these can certainly be caused by you know, squall lines. Multiple cells can cause them. Rain-cooled air. A lot of times in the field, you'll see what's called a shelf cloud, which is the picture on the right, and on the radar itself, it kind of bows out. We call this a bow echo, and that's the radar, you know, showing the reflectivity is being pushed out because of those strong winds. So that's something that you would see on the radar. The reason for that, things in Mother Nature don't just happen. If you have really strong winds pushing on a line of storms, the natural tendency is for it to bow out. The reason why it's bowing out, strong winds are pushing it out. So if we see those signatures, we'll be concerned that we might have a threat for strong winds. At the far right end of the spectrum, you don't have to have a supercell for a tornado, but we'll kind of go into it since it's a severe weather class. This is the classic supercell, kind of reversed from the image I showed you before, but the concept is the same. Air ingested into the storm itself, and then the rain cooled air on the front side. All right, that's what you get for talking too much. So this is the supercell again. We mentioned on the one side is you know, you have very warm moist air going into it. This is like the intake on an engine. Then the front side of the storm is rain cooled air. That's where you get your hail, high winds, and things of that nature. So supercell is like really like a full blown engine. Everything's working well. It's got the shear to maintain itself, and it can keep going. And on radar, we can see a supercell. On the left is the diagram, what it would look like in a textbook. And this is Atlantic Beach just a couple years ago. Again, this hook shape is the reflectivity. It's the rain wrapping around the circulation. So things in Mother Nature don't happen just haphazardly. This is an indication of the storm, you know, really spinning up. The tornado scale we use is the Fujita scale. You can see it goes from 0 to 5, with the worst damage being the higher numbers for sure. Contrast this with the picture we showed you before. Notice how these arrows are pointing toward each other, a convergent pattern. So it's not always that simplistic, but when we're on a survey, we determine two things. One is what's damaged, what's the wind speed, that type of thing. But whatever the pattern is, if it's convergent, a path, chaotic, that's indicative of a tornado, narrow path. If it's fan shaped out, divergent, it's more conducive with a microburst. So we're going to turn it over to you, especially since I'm choking up here. We're at the end anyway. Just to review, again, anything with rotation, that's when you report a tornado. If it's in contact with the ground, it's a tornado. If it's not, it's a funnel cloud. Any size hail we want to know about. Try to measure it if you can. If not, some type of reference. Don't use marbles because they all vary in size. Flooding, coastal flooding, city or urban or rural flooding, what's closed, how high is the water. Don't want you to get out there and measure it, but you know, you can give us a gauge for how high the water is. And then rainfall amounts, you know, anything significant we certainly want to know about. I didn't mention CocoRaHS. That will be in our link sent out tomorrow. That's a great program for young people or anybody interested in you know, precipitation reporting or to be more consistent. Our spotter program is only when you get bad weather. So chances are you're not going to be calling us much. CocoRaHS is more consistent, 7 to 9 a.m. every day. You buy a rain gauge, not a digital one, and you will report precipitation. Most days it's 0. If you got the app, it takes seconds. The days you get rain, you measure it, or snow, if we get snow next winter, and you send it on in. And then we stress the 800 number is certainly the best way to report that information to